Our project is diffusion through sand and gravel, and we are group 16V. And we consist of Katerina, Tiffany, Christina, Rin, and Stacy.
The motivation for our experiment is to familiarize students with diffusion through layers of materials and its impact on purifying water. A high school audience will be able to learn about and apply chemical engineering concepts to solve real-life problems like filtering water and making them aware of the practicality and importance of chemical engineers in an affordable experiment.
Starting off our experimental design, we have a list of materials made of two categories. One is to measure data, which consists of a pH probe, deionized water, and a buffer solution, and the other is experimental use, which is everything else like the scale, sand, and gravel.
The mass transfer principles driving our project have to do with diffusion and convection. Convection in this case is due to gravity, which is basically where water is being poured through the filter and it's not falling by itself. It's falling due to gravity, and that is what we consider convection. The diffusion portion is when the water starts going through the gravel and sand layers. The water is going from a high to low concentration, and we are removing particles from the system. When we remove particles from the water mixture, there is a buildup of dirt particles left over in the filter. Based on our results, we know that our gravel layer, where the water diffuses through in 42 seconds, is much more controlled by convection than our sand layer. This is because our sand layer is where there are much smaller pore sizes, but also many more pores than gravel. The water is slowly diffusing through that portion, which takes about 10 to 13 minutes as we recorded. This allows it to say our sand layer is the defining step for mass transfer to occur because it is our slowest step of the process.
The overall design and expectation is to take a dirt-water mixture and run it through a filter made of gravel and sand layers and have clear water at the end. In order to evaluate the effectiveness of this filter, we have qualitative and quantitative data. The qualitative data will be the change in color, and the quantitative data will be the change of pH as it was before and after it ran through the filter. To set up the experiment, we use the mass scale to measure out the sand, gravel, and dirt into bowls, and use a measuring spoon for the water. We also cut up 3 plastic bottles to create containers for filtration. Then using the dirt and water, we made a liquid solution and mixed them evenly together.
To get more into the experimental design, we chose to have 2 control trials, one with sand as the only layer and one with gravel as the only layer in the filter. So with one layer, we can see how much each material alone affects the filtration.
Afterwards, we did 3 trials with both layers in the filter and having sand as the bottom layer in all 3 trials. And for consistency, we used the same amount of sand and gravel and a uniformly mixed dirt-water solution being poured in.
This table shows the results of the control trials, and as you can see, the gravel layer only had the greatest pH difference and the ending pH with being most close to a pH of 7. This table shows the results of the trials from diffusion of dirt-water mixture through both layers. There was on average a 0.22 pH difference in all 3 trials, and in most of the trials, the ending pH was closer to 7 than the starting pH. So due to the average 0.22 pH difference and that most of the pH at the end were closer to 7, that means the water became more neutral as a result of going through the filter. And for some qualitative data, so before it went through the filter, it was an opaque dark brown mixture with some sediment mixed in, and afterwards it had a translucent tan color.
In the end, while the water doesn't look potable, it shows that diffusion still affects the heterogeneous solutions. This experiment showed that by diffusing dirt water through layers of gravel and sand, thus removing the impurities, can change water's property by making it more neutral. In the future, slightly acidic dirt water at a consistent temperature can be tested to see if a general pattern is observed and can further support the same conclusion.
This experiment has many applications to the real world. For example, chemical engineers often need to separate substances for various purposes. This could be anything from purifying or diluting a substance for commercial use to separating chemicals for research and design purposes. In addition, this is also useful for real-life emergency scenarios for anyone who isn't even a chemical engineer. When one is away from pure water, we now know that we can neutralize dirt water with something as easy to find as sand and gravel. So this experiment showed how simple it can be to neutralize concentrated substances, and we know that it has many purposes that one could use.